So we will start in a few minutes. Just giving a few more people a chance to get into class, okay?
Okay, sir.
Yeah. Okay, good afternoon, everybody. We should be able to start class now. We'll take roll in a little bit just to be sure we updated, okay? This is just a copy of last week's one. So we'll check that in a little bit. So last week we did, how do you call it? Topological sorts. Now, let's see where we are here on Canvas. Let's look at files. So if you remember last week, I had put up a final exam here as a sample. This was semester 2, 22-23, which would have been last year, January. Okay. So I'm hoping that everybody would have gone through that paper, and it has a lot of stuff about final exam, about what your exam would be like. It's not going to be exactly like that, but it's going to be pretty close. So today we said we were going to look at recurrence relationship, theta and omega. We'd review big O a little bit, and hopefully we talk about NP problems. You'll get a chance. And if anybody has any specific question, we could try to answer that. Does anybody have any questions about anything so far?
Yes, we actually had a specific question.
Go ahead.
So for the assignments, it was assignment 2. Let's pull it up. The question that asks you what the more efficient algorithm to be used. I was just wondering which algorithm we were actually supposed to use in that example, if there's any specific one or any preferred one.
For which part?
I believe it was part. Let's get the assignment itself. That was the
You're talking about this question here, right?
no, not the one with the weights.
That's assignment 2, bro.
I think it was the LCS question. So sorry, my bad. That was
That's what,
assignment 1.
assignment 1?
Yeah. The more efficient algorithm.
Let's take a look at it. I teach more than one course. So this one.
Oh no, sorry, sir. It was
All right, you're
It
taking up
was
a
quiz
timer.
2.
Tell me
It
clearly
was
what
quiz
it is
2.
you want. What's your specific question?
Quiz 2 part 3. 3 and 4
In
for
the
quiz
same
2.
assignment?
Nah, quiz 2. The one with the we were given a sorted set of n integers and another integer, and then you have to you're describing a brute force algorithm, but
Which
then
question?
where they ask you to describe a more
Question
efficient
2?
algorithm. The question 1 part 3 and quiz 2.
Question 1, part 3.
Yeah.
Right. So that's this problem here, right?
Mm-hmm.
Yeah. So ask me that question again. What it is
I
you
just
want to
wanted
know?
to know. I wanted to know which algorithm we were supposed to be using amongst the ones that you would have thought, if there's any preferred one.
Well, of course. You are given, you describe the brute force. You give a big O characterization of brute force. Then you describe a more efficient algorithm. So something that is better than the brute force one here. Yeah?
Yes, sir.
And then you give a big old characterization of it. I'm not sure what I'm missing.
But like which algorithm we were like in terms of the named ones that we had, like well I know it wouldn't be knapsack in this case because there
Oh,
was
hold
no
on, hold on. That has nothing to do with any of these. It's a problem that related to this problem. This specific problem. LCS not relevant here, knapsack not relevant here, topological sort not relevant here, triangle
right.
problem not relevant here. You have to look at this problem, look at how they do it. Okay? It's a sorted set of n integers, right? Which means that you have, like, let's say you have an array, right? It's sorted. So your numbers go in increasing order. Etc., etc., etc. Describe a brute force algorithm that determines whether or not there exist two elements in S whose sum is exactly X. So you have a number. Let's say you want to find out two numbers that add up to 25 or something like that. So you'll start with 3 and 5, 8, 3 and 12, 15, 3 and 93, whatever. Right? And then you'll try 5 and 12, 5 and whatever to see if you get this total. Yes?
Yes, sir.
So you can describe, whatever is brute force, if you know what brute force is. And then what is that big O characterization of that algorithm? So,
That'll be n squared.
well, you have to work that out. Remember, there's something for everybody to do, right? So I'm not saying whether you're right or wrong. That's something. And then for the same problem above, describe a more efficient one. Is there anything that is more efficient than brute force? That is better, faster?
Like would this be generalized like you would say like greedy or
Well, no, you have to describe how you will go about it. I'm not looking for a name. I didn't ask you
okay.
to name an algorithm. I said describe a more efficient algorithm, which means you'll give me the steps of what you will be doing to get it.
Oh sorry, that's given the step by step. It's not like a
Well,
specific
that's the
algorithm.
algorithm, isn't it?
Yeah.
I didn't ask
Yes.
you to name an algorithm. I don't want the name of an algorithm.
Okay.
Yeah.
So if I
And
was
then
to like well, for example, like if I was to use hash tables and as a solution to the problem, would that
hash
be
table is a
acceptable?
data structure,
Well, I mean
right?
like
So
using a
if your
hash table
algorithm call for a data structure that is faster, fine. But remember, it will take time to build that hash table. That adds to your step in your algorithm, eh?
right.
So like if let's say it wasn't sorted and you wanted to sort it and then do it. So even if the step after it's sorted is real short, the sorting is work too, you'll have to count it. But this
Yeah, the
says that it's
constant.
already sorted. Okay?
Okay. Mhm.
Is that all right?
Yeah. I guess you answer my question.
Okay,
Yeah.
very good. Anybody else, class?
Yes, sir. When you say describe an algorithm is not, for my answer, I listed the algorithm that I would have used and described it, but you have just preferred the description without the actual algorithm.
When we say describe an algorithm, it means tell me step by step what you have to do,
Okay. So
right?
it's not necessarily that you wanted the algorithm itself. You just
Yes, I
wanted
want the algorithm itself. I don't necessarily need, when I say describe, it don't mean that I need the language what to do.
Okay, thank you, sir.
Does that make sense? I do expect you to, when I ask you to describe a brute force algorithm, what do you take that to mean? And you're going to tell me the steps in how what you do to check brute forces to check every possible option, right? So when you're going to describe how you're going to check every possible option. Yes?
Yeah.
Right. So if I say describe an algorithm, it means tell me all the steps. So by my using the term describe a brute force algorithm, it means I'm not asking for you it in pseudocode like this, right? This is pseudocode. Okay, yes, this is the algorithm, but I don't want you to give me code. I want you to describe and tell me what is the step-by-step kind of thing to do. If you prefer to write code and you could write code, that's fine. I'm trying to make it easy for you. Does that make sense, class? Did I confuse you?
No.
Now, the only way to do this is to sit down and write out put a set of numbers in sequence and try to work it out and see what is the best way to do it. You want two numbers that add up to a next one. Okay?
I so you hear me properly?
Yes, I am.
Somebody anyway to them, right?
Okay, thank you.
No problem.
Any more questions, please, people? I want you to be clear about what you have to do. Make sure and submit everything as early as you can. Now, today's your last class. And your exam, well, your exam is a couple of weeks away, but the exam is not the deadline for this. When exam reach, I am marking assignments. So when I mark assignments by whatever date, if your assignment not there, that's it, because I'm sure that your deadline will be passing. So be careful, people. Please just make sure and get your stuff in. Okay. All right, good. So, where are we now? So we said that we have to do recurrence relationship, theta, omega, whatever, right? Now we were going to talk about big O. Yes? Anybody has any questions about big O? What questions do you have about big O? Did you all understand your big O stuff?
I was wondering if there was a easier way to calculate the notation.
When I say calculate the notation, I don't understand what you mean.
Well, when we have to decipher whether or not or what the order of a certain algorithm is, sometimes it could get confusing when they're nested loops or
Right, yeah.
like
Yes,
certain things like
yes, it
while
does.
statements.
I
So I was
agree
wondering,
with you. It can be confusing and students have a hard time with it sometimes, but that's part of the skill that you have to learn in the course. So I don't know about an easier way or something. You have to be able to check it, to count it by looking at the steps and seeing what you do. Yes?
yes, sir.
So sorry, you have to know that. So let's take a look at this set of slides. I'm not sure, I can't remember if I did it with you, but it should help a little bit. Let me see, what's the name of this file now? Right, big O analysis, and let's see our slides, our files. If we have big O analysis is up there. and Analysis of Algorithms, Lecture 1, right? So we're just going to do a quick review of this. I think somebody had asked me for it. Okay. So we're saying that an algorithm is a clearly specified set of instructions to solve a problem. So when I ask you to describe an algorithm, I want you to give me that set of instructions. But by using the word describe an algorithm, it means tell me what to do, describe the steps that you have to carry out. Okay? But I'm not asking for you to write code, pseudocode, or Java code, or any kind of programming code. Tell me step 1, do so and so, step 2, do so and so, step 3, do so and so, right? That is an effort to make it easier for you so that you focus on telling me the algorithm rather than having to worry about how to write it in code. Because from moving from your steps, your description, to writing code, that's another skill. So the course is not a programming course per se. So I'm not asking you for code. So when I tell you describe an algorithm, give me that clearly specified set of instructions, step by step, but in normal English language. The resources we consider in when we're looking at an algorithm to see if it's efficient or not is time and space. The time is processor time, and the space is the amount of memory required. This course really though focuses on the amount of processor time required. Okay, the amount of work that the processor has to do in terms of time. The running time of an algorithm is almost always independent of the programming language or even the methodology we use. What might happen sometimes is the algorithm might be a little bit more efficient depending on the data structure, the type of data structure we choose to use. Whether it's a tree, a graph of a tree, somebody talked about a hash map and so on. Okay, different kinds of data structures, an array as opposed to a tree or what have you. So what does it depend on? Depends on the amount of input. The running time is approximately equal. This means, approximately equal to the size of the input. It's a function of the input, right? That's where we get the function f of n. So n is the size of the input, the number of values in the input, okay? The value of this function depends on different factors like the speed of the host machine, the quality of the compiler, the quality of the program sometimes, okay? Suppose an algorithm for processing a retail store inventory takes 10,000 milliseconds to read the initial inventory from a disk. Now 10,000 milliseconds is 10 seconds, right? Because 1,000 milliseconds make up 1 second. So 10,000 milliseconds is 10 seconds from disk, and then 10 milliseconds to process each transaction, right? A transaction is a sale or when you sell something or you buy something, right? Processing n transaction will take 10,000 plus 10 times n milliseconds. So even though 10,000 is much, much greater than 10, we sense that the 10n term will be more important if the number of transactions is very large. Because if the number of transactions is small, then this is more important. But let's say n is now, let's say we want to process 100,000 transactions. When you multiply that by 10, you'll get 10 million. So this 10,000 is the initial start, but this is now 10 million. So obviously this is more important than this part. Okay? Stop me if I say something and you need it clarified, right? These coefficients may change if we buy a faster computer or a disk drive or use a different language or compiler. But the goal here is to express the speed of an algorithm independently of a specific implementation on a specific machine. Specifically, it means okay? Or the chipset, right? Or the special, whether it it uses not hyperdrive, this other thing, you know. We're not interested in those because the computer might be faster, but what is important is the algorithm itself. So here the constant factor is ignored. Why do we ignore the constant factor? Because as n gets very large, right? As n gets very large, this part grows as n gets bigger. And this stays constant. So if this stays constant, let's say it's there, and n is getting very, very, very large, right? After a while, this becomes to pale in significance, right? So think about it, it's like this, right? Let's say, yeah, you buy a vehicle, right? Now, when you buy the vehicle, it costs you a certain amount of money, right? A down payment, right? Now, it might be very difficult for you to make that down payment because let's say the down payment is $25,000, right? That seems to be a lot of money. It's a very difficult hurdle to get across. And your installment might be $5,000. And they say, well, the installment is much less than that. I could make that installment. But then what happens now? Remember, this installment is every month, month after month after month after month. Okay. And after, let's say you took the loan for 8 years, that's 8 5 4, 5 12 60 by 8 is $480,000. So when the installment was looking like real big, the amount of money you pay over time is much, much more significant. And then we started talking about maintenance yet. Because I know I have one friend, she bought a Mercedes Benz because she thought that was the best thing ever. And she put out the money and she put every cent she has in buying that Mercedes Benz. But after a little while, a couple of years using it and whatnot, she needed to change brakes, the disc pads and the brakes, right? But the cost of it was so high that she did not have money to change that because all of her money went into this year. And she didn't factor in maintenance and when you change oil and you have to do things by the company to maintain the warranty and so on. So she eventually had to sell the car because the maintenance was ridiculously high. The point I'm making is sometimes these little things add up and they grew and they grew and they grew. And what seemed big now pales on the side. Okay? So that's why here, this 10,000 milliseconds to read from the hard drive, it takes you 10 seconds, and it feels like a long time you're waiting. And then this looking so small, this 10,000 and this is 10N. But as 10 gets larger, then it gets this part becomes much bigger. Here, the constant factor is ignored because of that. As it gets smaller with the technology improvement, you get rid of the hard drive, the old disk technology, and you get a solid state drive. Well, the solid state drive is so much faster where it was taking 10,000 milliseconds to load that it might actually take just 10 milliseconds to load into memory from a solid state drive. So it gets smaller, that constant factor gets smaller with the technology improvement. But as n gets large, the number of transactions get large, the algorithm still takes longer to carry out, right? As it, depending on the kind of function, whether it's n squared or n cubed. So big O notation is the upper bounds on running time or memory. Where's upper bounds? The worst case scenario. And we talked and we gave a lot of examples why worst case scenario, the upper bounds is more meaningful than average case or best case, right? When you go by the doctor, right? If you have elderly parents or grandparents and so on, and they go by the doctor, and they tell you, well, yes, if you have the surgery, you're going to get better, you'll feel really good. But then they spend a long time talking about the risks involved, the risk factors. Did you ever look at those advertisements for medications on cable? Right? It takes you have a 30-second commercial and they spend 5 seconds telling you about how good the drug is and how much better it works than whatever it had before, and how your quality of life is going to improve. And they spend 25 seconds on what are the potential side effects, the conditions under which you mustn't use it. You can't use it with this drug and that other drug. And if you have this previous condition, you can't use it, tell your doctor about it and so on. So there's more time spent on the side effects and so on, because those things, the worst case scenario is absolutely more important, because somebody might prefer to live with the sickness than to be cured of that sickness, but you get something else much worse. Yes? So you have to always look at the worst case scenario. You have to be careful. You have to factor that into making your decisions. So big O notation is used to say how slowly the code might run as its input grows. Because when we say how slowly it runs, the algorithm still runs at same speed, but it takes longer to get a result. Yes? If you're building a house with 2 bedrooms, you might get the complete house, let's say, in 2 months or 3 months. But if you're building a house with 10 bedrooms, well, it might take you a year, right? My neighbor building a house a year and a half now, and it's taking time, because there are all kinds of things that could go wrong. The more things you're doing, the more it could go wrong. So your stuff could get slowed down to get a result, to reach the completion. And if you're doing something with 25, 30, 50 rooms, well, how does that time grow? Yeah? And what are all the things that could go wrong and keep you back and so on? So you have to be careful with that. So big O notation is used to capture the most dominant term in a function. What do we mean by a most dominant term in the function? That item that causes the greatest delay or makes the most contribution to the way the code runs. Okay? And to represent the growth rate. It's represented by big O, capital O. So let n be the size of input. The running time of an algorithm is T of n. And T of n might be a function of n, right? Simply n, like if it's 5n, 10n, 100n, we'll simply write it n because the constant doesn't contribute to anything. We know the time will grow as n grows. So we say that T of n is in the order of the function of n if and only n the running time is less than or equal to this function multiplied by some constant whenever n is big for a large constant c. And that is where the scientific definition of big O comes in. So how big is big? It's big enough to make T of n fit under this. So T of n will be less than that, which means that this is a worst case scenario for the running time. How large is C? Large is enough to make this fit there. So C is large enough and n is large enough so that this figure is bigger than this. So remember, we had a running time of 10,000 plus 10n. Let's say f of n is equal to n and c is equal to 20. Right? Excuse me. Now this graph here is in logarithm. That's why I look in so thing, right? As these functions extend forever to the right, their asymptotes will never cross again. So n is big enough means it's bigger than this figure, because less than that, it's the opposite, right? Because this is greater than this. But once you pass this 1,000 figure, then you'll find that this is the upper bound, meaning this is bigger than this. Okay, so T of n is in the order of f of n. And we did all of this before. We went through the formal definition, so you all could go through that and review those things. Okay, we did all of this and we had many functions. These are all functions of n, and they are different kinds of description for them. We went through this and we saw what is best and what is acceptable and what is horrible. Okay. So what we look at now is omega is a set of all functions T of n that satisfy this. So it has all this definition and thing, right? But there's a simpler way to look at it, right? Omega gives us a lower bound on the function. Remember, big O gives us an upper bound, right? That's the worst it could be. Omega gives us a lower bound. It tells us the best it could be. Your algorithm is at least this good, right? This is the at least as good as the best it could be, right? Or big O says your algorithm is at least this good. Omega says your algorithm is at least this bad. So a big O gives you the worst case and omega gives you the best case. So 1 second, I just realized this light is off. Sorry. So it's not a secret, it's just that the light with this here, I don't deliberately mean to make face blackout. It's just the window is behind me. That wall is also a window. So if I go there, the same thing would happen. And if I put a light on like this, where you all could probably see me, then it's dazzling in my eyes. So it's very difficult to tolerate that. So it's not really important for you to see my face or such. I know that would have been better, but I don't get to see any of you anyway. So I think we are accustomed with this. So yes, hopefully the light is a little bit better at least. So big O says your algorithm is at least this good, right? Which means that's your worst case at the very least, right? And your omega says your algorithm is at least as bad, which means that that's your lower bound, your fastest time, your best case. Theta, now they spell sandwich between, so that's what happens when English is not their first language. Theta is between best case and worst case. It's a set of all functions that are in both of these. So that is when your big O and your omega is the same function. Okay? So there might be different constants, one to take it at the higher level and one to take it at the lower level. So this here is the simplest way for you to understand theta and big O and so on, right? So we know big O, right? If they are positive constants C and N0 such that the running time is less than or equal to this, right? Big omega is if they are positive constants C and N such that the running time is greater than or equal. So remember big O, the running time is less than or equal to this, okay? Which means that the big O function is above and this your running time is somewhere here. So big O is your worst case. Omega, your running time is greater than that, so that omega function is below. That's your best case. Because remember, as you go up, the running time is bigger, right? So big O is higher than your actual running time, and omega is lower than. So omega is your best case, and big O is your worst case, and your running time is between these two. Okay? Big theta is if and only if T of n is equal to the order of f of n, and T of n is of the omega f of n. So if the two of them is the same, then we can use big theta. And little omega is if and only if this is not equal, your running time is not equal to theta, little theta. So there's another simpler way to put that. Let's see if I have it on the next slide. Right, look, big O, the running time is less than or equal to the growth of this function. Omega, big omega, is the growth, the running time. The growth of the running time is greater than that same function. Big theta is the growth of T of n is equal to the growth of f of n. And little o is if the growth of T of n is less than the growth of f of n. So we have another way of making that easy. I will show you just now on the original slide. So you have worst case versus average case. I went through all of that with you, right? The worst case is when the longest possible time. Average case is when we look at all the possibilities and so on. We can get an idea of what that average is. In this course, we focused on the worst case. So these are some examples and what have you. You could read those. We did binary searches and so on. So you can go through this in your spare time. Right? Now, excuse me. Let me see if this has the one when I told you I would come back to big omega and theta. Let's see. So you could go through this in your spare time. Let's see if we go back to where omega and theta is and so on. Which is lower down. Now remember there's your scientific notation here, scientific function. Right? Now remember we said f the given functions f of n and g of n. We say that f of n is of the order of g of n, which means the same kind of running time, right? It's less than the than this g of n if they are positive constants c and n0 such that the f of n is less than or equal to c times g of n, but this value of n greater than or equal to n0. That was where they crossed n0. But you could find any value we could use that shows that it will work. I went through that with you. So if we continue now, remember that thing, right? Okay, it's not in this one. Let me see if I have it here. Share this with you. So remember, okay, where's my big O now? Right. So remember the big O notation is where this is less than or equal to, right? Okay, so Fn is a big O of G of n with less than or equal to. Now, we will go down further. I should probably put this up and let you look through it. It's the same functions and so on. Now, remember where big O was less than or equal to omega is, greater than or equal to is the same thing, but this is greater than or equal to. Big theta right here, big theta is simply the same thing. C is less than or f of n is greater than or equal to this, and f of n is less than or equal to a similar function. What is different? The constant is different. Remember, I told you the one on top will be one constant and the one underneath is another constant. So then big theta is when you are bound by the same function. Your best case and worst case is the same function. That's big theta. Okay? Little o, right? The difference between big O and little o, right? There's an integer constant, just looking the same as that one, it. Little omega, there's a little mistake here. Little o, right, doesn't have this equal sign. And little omega doesn't have this equal sign. You see in here, big omega, f of n is greater than or equal to c times g of n. Little omega will be f of n is greater than c times g of n, no equal. So this is not correct in this slide. And little o is less than. Big theta is where worst case and best case is the same function, but the constant might be different. Little o is just like big O, except for this equal. And little omega is just like big omega, which is best case, but without this equal. I have it on another slide somewhere. It would be on one of the slides you have been given. Plus, you will see it in the textbook. And that's why I told you it would be easy just to look at that. So they give you some examples here for omega and thing. So there's little omega here. But for our purposes for exam, you don't have to worry about omega and theta and little o, right? Those are just little variations of the same idea. Once you understand big O and you're aware of theta and omega and thing, I'm happy about that. Okay? So we're going to take a look at recurrence relationships now. So I have a couple of those. Fibonacci, Towers of Hanoi. I don't know if you all ever played the game Towers of Hanoi. Right, so let's take a look at this slide. Remember I told you this course takes effort to follow, and you had to be keeping up to date with your reading and practicing. So nobody ever said that this course was going to be easy, but we did say that if you do what we tell you to do, you should be able to pass comfortably. There are people who have gotten A's, very few, but they have gotten A's. So we're looking at some recurrences and so on. Right, now we review asymptotic notation. Remember, upper bound was big O, right? Same thing, scientific notation, if they exist positive consonants, etc., etc. Now, this here says it in English. A function of n is of the order of g of n if there exist positive constants c and n0 such that f of n is less than c times g of n for all values of n greater than or equal to n0. So this has very few symbols in it, right? No big thing. But this one has more symbols. So formally, right, this here means the same thing as this. Let's see what it says, right? Formally now, right, functions of the order of g of n is equal to the set of functions such that there exists, this wrong side E means there exists, and you know this bracket here means the set of, right? And this colon means such that. So if you know that, we read it now, right? The set of functions of the order of g of n, right, which could be whatever, is equal to the set of functions of n such that there exists positive constant c and n0 such that f of n is less than or equal to c multiplied by g of n for all. This means for all n greater than or equal to 0. So when you see this notation, don't panic because, right? I mean, you're supposed to feel yourself feeling brighter if you could read this. I don't know. This means the set of, okay, the set of what? The set of functions of f. This means what? Such that. See it? Such that. Okay? This means there exist. Look here. There exist positive constant c and n0, right? And this means for all. Look at here. So it's nothing fantastic or strange or unusual. It's just that you tend to get a block when you see all these symbols. But if you take your time and analyze it properly, you'll have no problem. So here's a big O fact. A polynomial of degree k is of the order of nk. So if we say degree 2 is when you have an order of n squared. That's all. The degree of the function is squared. The highest power is 2. The degree of a expression is the highest power of the variable. So even though you have a squared, or sorry, x squared plus 3x plus c or whatever, x, the power of x is 1, the power of the first one is squared 2, the degree is 2, the highest one. Right? Now, asymptotic lower bound is omega. Remember, we say lower bound is the best case. So we read it again. A function f of n is of the belongs to omega g of n if there exists positive constants c and n0 such that c times g of n is greater than or equal to 0, but less than or equal to f of n. For all n greater than or equal to n0. Remember when you had to look for that value n? So this discussion here, if you have not done any of your work, right, then this will be totally Greek to you, literally. Okay, if you have been following your work, then you would have not much problem following it. It might be a little tough given your experience or your fear and whatnot, but it shouldn't be totally Greek to you if you have been doing your work. Okay? Asymptotic tight bound. A tight bound is of theta when the upper and lower bound is of the same function. See it? Here, the upper bound is of the big O and the lower bound is omega. So a tight bound is theta when both of them is the same function. The difference is one constant C1 here and another constant C2. So this C1 gives, when you multiply it, you get a value above. This C2, when you multiply it, you get a value below. And your function is somewhere in the middle here. So this is your upper bound. And this is your lower bound. So if the function is in the same form, then it is a tight bound. So theta. So theta means big omega, and big O is the same function. That's all. Now, I think I'm making sense and I'm clear, but of course, if your mind is not ready to receive it, it will just pass over your head. And this is why, for the last 13 weeks, I've been exhorting you and encouraging you and pleading with you not to let a week pass without doing work. So other asymptotic notations, as we said, was little o, right? And little omega. So remember in this slide now, you notice what is different about the other slide? The less the equal part. That is not there, right? The equal part is not there. See it? Now, the two signs looking the same, right? But they're not the same. This one says f of n is less than c times g of n. This one says c times g of n is less than f of n. So if we turn it around, we'll be say f of n is greater than c times g of n. So O is when f of n is less than c times g of n. Omega is when f of n is greater than. But the difference is with big O, there's a less than or equal. With little o, there's no equal. With big omega, there's a equal. With little omega, there's no equal. Okay? So this slide makes that very clear. And the same language is here. So intuitively, little o is like less than, big O is like less than or equal to. Big omega is like greater than or equal to, little omega is greater than alone. Theta is like both omega and big O. Okay? That's all. So if you understand that, that's why I told you in the beginning that once you learn big O well, the rest will become easy because you can see them in terms of big O. Isn't that cool? And I told you that wouldn't be much. And I'm not testing you on this, but you should understand it. So what is happening here? This is merge sort. We went through sort. Merge sort is a recursive method because it calls itself. Okay? Just like factorial and power function and some of the others that we did, right? So what here, if we look at this, you will see the time for merge sort is T of n for a function. T of n means the number of items you're going to sort. When you break it up in two, you will see that this operation is one time, okay? This operation is also one time unit. And here, because we split and merge sort, we split it into our first half and a second half. You will see the running time for the half is T for n over 2. Whereas the whole thing is T for n. That's not that the time is half. We're not saying the time is half. We're saying the time for half. There's a difference, right? Because if you're building a house with 2 bedrooms and you're building a house with 4 bedrooms, do you think the time with 4 bedrooms will take twice the size of a house with 2 bedrooms? No, because the house with 4 bedrooms still has kitchen and toilet and carport, right? In addition to the 4 bedrooms. And the house with 2 bedrooms also has carport, 4 bedrooms. The house with 4 bedrooms is not necessarily twice the amount of the house with 2 bedrooms. So what's happening here is that if we're doing half the amount, it doesn't mean that it will take half the time. And that is what we're going to look at here. So if the time for an operation is 1, when n is equal to 1, meaning if you're going to sort an array or whatever that has only one value, it'll take one operation. But here, the time for the whole thing is equal to 2 times the half, the time it takes for half, plus the time it takes for n. It's like the bedroom. So you have the 2-bedroom house, and you have a 4-bedroom house, right? Remember the 2-bedroom house is kitchen, dining room, bathroom, carport, etc., plus 2-bedroom. And the 4 bedrooms here is kitchen, dining room, bedroom, plus carport, plus 4 bedrooms, right? So what's going to happen is the amount of time this will take is the kitchen, dining room, bathroom, and carport plus 2 times this part. See? This part will actually be constant. It might be the same here. So this part will be a multiple of that part plus this. And that's what this is saying. So this part here, right? This part is a multiple of this part plus this part here. Because that's the way the thing works with the algorithm. So the expression for this operation here is we look at the time it takes for 1, the time it takes for half, and plus whatever any constants or any other issue. So what, in a more brief or clearer way, is the running time? Well, we could look at it here. Now we call this a recurrence because remember this is recursive, right? So the expression this here is an expression of what happened on the slide before. So this expression is a recurrence. A recurrence is an equation that describes a function in terms of its value in smaller functions. Because if you have a big array to sort out, merge sort says divide this into 2 and sort this half and sort this half. And here's what. When you go to sort this half now, it says divide that into a further half. And you keep dividing and dividing and dividing until you can't divide no more and you have only 1 item. And if you have only 1 item, then that takes, see, 1 time, it takes a constant time. See? So when we run it, when we divide it in 2, we'll see it have 2 times the time it takes to half plus that constant for n items. Any questions on this? So here are some examples, some recurrence example. This one is here where we adding a series of numbers, right? Let's see if we could understand what this means. If we're adding a series of numbers, okay? So my intention, by the way, guys, tonight is to finish a little early with you, all right? So in order for you to feel that we finish early, I want to not bother with the break, if that's okay with you. Yeah? And we'll go through and we'll finish pretty early. We almost finish what it is we have to do. Okay? Now,
Okay, sir.
is that all right with you guys? Yeah?
Yes, sir.
Thank you very much. So this here is we adding a set of numbers, right? We're adding a series of numbers together. And what this says is if we have no numbers to add, if n is equal to 0 with no numbers to add, we take no time. Isn't that cool? Yeah? We have nothing to do, no operation. Sorry, I shouldn't say no time. I should say no operation. There's no operation to do. But once n is greater than 0 and we have to add, right? It'll take a constant amount of time to add 1 number, and then we'll have n minus 1 numbers to add because we add with 1 number at a time, right? Yeah? So if we add, let's say 2 plus 4 plus 9 plus 16 plus 3 plus 8. How are we doing that? And we start with some value, we keep our total and we head, well, we have none, right? So then we add 2. So our total is now 2 as that constant time. And then we still have all this to add up yet. And then when we come now, when we have this to add, we will have 4 plus the balance. Okay? So here is another series. Same thing, no time, right? But we can have n for that amount of time plus the rest. Okay? So there are two different series. One takes a constant for one, and this one is whatever n numbers is, we have so much because we add in all them numbers. Okay, now the time for this operation here, with this process, let's take a look at it, the running time. If we have one item to add, it takes that constant time. And if n is greater than 1, what we'll do is we'll take half that time. Sorry, not half the time. We divide the thing into 2. So we'll have 2 halves. So it'll be the time it takes for 2 halves, 2 times that, plus some constant. This one is a little bit different operation for this one, right? The way this one operates, look at it. If we have one item, we have that constant. Here now, if we divide it into however many parts, we'll have A multiplied by the time it takes n over so many parts, plus a constant by n for all n greater than 1. So how does this help us? Let's take a look and see. So the point about this is that these operations can be represented. These times, various operations and algorithms, recurrent algorithms, can be shown in different ways for the running time. So if we're solving recurrences, there are different methods: a substitution method, an iteration method, a master method. So I'll just go through this with you. I'm not testing it on testing you on it this time, okay? But you still need to know it, okay? And I know some of you are breathing a bit better and not starting to hyperventilate because I'm saying I'm not testing you on it. If I were testing you on it, we would spend much more time doing more examples on it. So the substitution method, also known as making a good guess method, is to guess the form of the answer, then use induction to find the constants and show that solution works. Some of you may have used induction in previous math classes, and we call it PMI. Have you ever heard of PMI? Principles of mathematical induction. Okay. So how does this work here? Right? We have the running time is equal to 2 times 2 multiplied by the time it takes to do half and some constant. Okay, so here that gives us the running time is of the order of n log n. Why is it log n? Because we keep dividing it by 2. And if we keep dividing, then you see in log, because just like the binary search or the coin problem, we kept dividing by 2. So log n is even better. But because of this n, we multiply by n. So n log n is much better than n squared, right? And this here is, this symbol means the floor of n over 2. Okay? So what is the best time for n over 2, right? So n is n of log n. Now here we have a constant coming into play, the 17. What if it was a constant instead? What it will be? It will still be of the order of n log n because we have a way of ignoring constants. Another option is what the book calls the iteration method. You expand the recurrence, work some algebra to express as a summation, and evaluate the summation. We're going to look at a few examples, right? Look at this one. Remember, we saw this one earlier. Yeah? We saw this earlier. So if n is equal to 0, there's no thing it takes 0 time. If n is greater than 1, it'll be c. If n is greater than 0, sorry, it'll be a constant plus the balance for n minus 1. So 1 taken away from it. So how does this work? S of n is equal to C plus S n minus 1, right? So this here is the general form. Okay? And you'll keep taking away 1 until you reach 0, and that will be a stopping condition. But if we use this general form, what will S of n minus 1 take? So let's say n was 10. This will be C plus 9. What form will this take? It will be the same thing. This part will follow the same because it's recurrent. It's going to be look exactly like what this does. So this will be C plus S of n minus 2. And this will be C plus S of n minus 3. And we'll keep taking away 1, and we'll keep adding C's. But how long will this go? How far will this go? If we keep taking away 1, what will be the last place? What will be the value at the end? S of what? Anybody? What will I get? 9, right? And then I take away our next one, I will get 8. And then I take away 1, I will get 7. When will I stop? When will I be able to stop?
At 0.
0.
Thank you very much. I was going to cry if I had an answer, man. Because if you keep taking away 1, 1, 1, 1, you must end up with none at some point. Right? That's basic thing. If you have money in your pocket and you keep spending and you're buying things for $1, right? $1 study for something. You really like some kind of chocolate or something. After a while, you'll end up with $0. You'll have to stop. But what happens is every time we take away 1, we add a C. So how many C's will we have? How many times could we have taken away 1? N times. So this part here will have 0 like this piece up here. But how many times will we have C's? We will have 10 C's, or how much ever n was, right? So we'll have C times n. So this algorithm will take C times n, but C is a constant. So we really don't care whether this is 2 milliseconds or 5 milliseconds or what. We could simplify this to n. So it will be of the order of n. Let's take a look at that and see what they do. See? So this part here, this part was written as C plus S of n minus 1. So this C is brought down here. So this part takes the same pattern as C plus S of n minus 2. Okay? So you get 2C plus S of n minus 2. And then you get 3 C's. And you keep doing it. Same thing until at some point you have K some value somewhere halfway, right? It's KC plus S of n minus K. When will we stop? Right? We will stop when K is equal to n. So you'll get when K is equal to n, what happens? You'll get NC or C n times C, but we know we write it in alphabetical order, right? So it'll be C of n plus S of 0, which is equal to Cn plus 0, which will be equal to C of n. And I say we ignore the constant, so the operation will be of the order of n. So this K is some constant representing some value anywhere in the process. Okay? So far, for n greater than or equal to K, we have that. But what happens if K is equal to n? See? So this process is, we'll see that when n is equal to 0, the time is that. So in general, S of n is equal to C of n, right? Here's another example. Remember the other one in the beginning, we had 4 examples. Very good. So this is the one we just look at. Now we're looking at this one, right? N plus Sn minus 1. So we start with S of n is equal to n plus S of n minus 1. So what will this one be equal to, class? If we're using the same pattern, right? So we have S of n minus 1 of n is equal to n plus S of n minus 1. What will this be equal to? What will I write underneath here for this part? It'll be n plus what? Anybody? This value here comes here. And then this value comes here with minus 1, 1 less. So if we follow that same pattern, what's going to happen here? This value will come here. It'll be n minus 1 plus what? This value 1 less. So S of n minus 2. And if we keep going, this will be equal to what? Well, we'll have n plus n minus 1 plus n minus 2 plus what? S of n minus 2 minus 1 is n minus 3. Because this here is n minus 1, that's this value, minus 1. And this here is this value, n minus 2, minus 1. So what's going to come next? We'll have n plus n minus 1 plus n minus 2 plus what? N minus 3 plus S of n minus 4. So if n was 10, you realize this would be 10 plus 9 plus 8 plus 7 and so on, all the way down till what? 0 and yeah. But there's an intermediate step, right? Okay. So this will be n plus n minus 1 plus n minus 2 plus n minus 3, right? Plus S of n minus k. Right? And then when will we stop? Remember, if you look at the top here, you will see n is equal to 0. And when will we get k at the end? What if k is equal to n? We'll get S of n minus n, which is S of 0. And what would we have all the way down to 0? N plus n minus 1 plus n minus 2 plus n minus 3 plus n minus 4 all the way down to 3, 2, 1, 0. Okay, and what if we add up from n plus n minus 1 and so on all the way down to 1? Anybody remembers how that works? We added up 1 to n. You remember that? It's the first plus the last, n plus 1, right? Multiplied by the number of items, which is n over 2. And which is equal to what? N squared plus n, n squared plus n over 2. And you realize that what we do is we ignore the constants and we ignore the lower terms, and this will be of n squared. So this process will be of the order of n squared. Let's see what they see. See if I get it correct. See if I know what I'm talking about, or it's just Greek to me too. right? So the last term here would be k minus 1, and over here will be n minus k. But, so this really, if you look at it, they introduced this new symbol, and if you did your maths, you will know this is the sum of all I from I equals n minus k plus 1 to n plus s of n k. N minus k, sorry. So that's for n being greater than or equal to k. But what if k was equal to n? We'll have the sum of I from 1 to n plus 0. And we got this just now, which was the first term plus the last term multiplied by n over 2. So you'll still get the same thing, n over 2 into n plus 1. Same thing. So in general, the sum of n is equal to that. So here now we're looking at the running time. Okay. So when n is equal to 1, if there's only one term, the running time is a constant. But if we time for half, so that's 2 halves plus this for all n greater than 1. So we'll keep dividing by 2 until we reach only one item and we can't divide anymore. And that is where we'll get the C. So what happens? The running time is equal to this. So what's going to come next? We're following this pattern because it is recurrent. So what happens? You will see this, right? This is half multiplied by 2 plus C. So we'll get here now 2 into what? Right? Here will be 2 times what? It'll be t times n over 4, right? Times 2 plus c. So this here would be equal to this part plus c. So this here became this. So now this part here is what this is. All right. So before I go further, let's make sure that this is correct. See, you take this now. This here is twice by half plus c. Yeah. So if we multiply it and we work it out, this will give us 2 2s are 4 times t of, I'm going to put them in brackets. 4, 2 2s are 4 times t of n over 4 plus, now this is 2 of this, so there's 2 of that plus 2c, right? Plus this c. So that will give you 4t of n over 4 plus 2 and 1 is 3c. See, over here had 2, but only 1c. Now over here has 4, but 3 c's, 1 less c. Okay? Let's go again. See? And of course, we could go, and we'll go until we see some value of k. Right? K is less than or equal to n. So if we replace n with k, right, we will get something like this. 2 to the power of k, right, plus t of n over 2 to the k plus 2k minus 1c. Notice the 1, right? So here, right, this is 2 squared, which is 4. So this is 4 minus 1. This here is 8, 2 to the power of 3 is 8, 7 is 8 minus 1. This is 2 to the power of 4 is 16. The denominator is 16, so this is 16 minus 1. So if we're using k, we have 2 to the power of k here, 2 to the power of k, and this will be 2 to the power of k minus 1 times c. So what we're gonna do? Will we put k is equal to n? What do you think we should put k equal to? Because we have powers of k and so on, we should use, we keep dividing by 2 every time. So when will we stop dividing? Right? We will stop dividing. We will reach a point when n is equal to 2 to the power of k. See it? So n over 2 to the power of k will be equal to 1 if this is the case. If they're the same, then a number divided by itself will be equal to 1. So what will k be equal to, the math people in class? The people who understand their maths. If n is equal to 2 to the power of k, what is k equal to in terms of n? If 16 is equal to 2 to the power of 4, and 2 2s are 4, 2 is 8, 2 16. 32 is equal to 2 to the power of 5. N is equal to 2 to the power of k. What is the relationship between this and 16? What's the relationship between 5 and 32? What's the relationship between k and n? I am sure I taught you this before in one of your previous classes. Either network architecture, I probably teach some of you computer networks, or in Java, when we did recursion, I would have mentioned it, but I will take more on. I like my granddaughter, she's 5 and don't take more on, so. And yes or no? I'm kidding, guys, don't take it personally. What happens here is k, if n is equal to 2 to the power of k is equal to log n in base 2. Because the log of a number is the power, the log of 16 is the power that the base must be raised to get that number. So we raise 2 to the power of 4, the 2 is the base, 4 is the power to get that number. 2 is the base, 5 is the power that we must raise 2 to get that 32. So k is equal to log of n. Right, guys? So what happens if k is equal to log of n? So far for now, n is greater than 2 to the power 2k, because we keep dividing by 2, right? So we have this generalization, which is the same thing here. This generalization is what we bring across here. But what if k is equal to log n, right? When k is equal to log n, then this part here, right, 2 to the power of k is equal to n. So this will give us 2 to the power of k will give us n times t of n over 2k, n divided by itself will be 1 plus n minus 1 times c. But t of 1, look at it here, the running time for 1, t of n is 1. So this means t of 1 is c. So this will be n times c, which is cn. Well, let's put that there. N times c plus n minus 1c, right? Which will be what? If we factorize, we'll get c into n plus n minus 1. Are you seeing that? We factorize, we take out the common factor, and this will give us c into 2n minus 1. Let's see what they will tell us here. We continue. So obviously, log of n is coming into our factor here. C2 to the power of log n. And anything to the power of log n, right, is n. So t n over n, you'll get n t1 plus n minus 1c. And this is n, and that's what I had just now. C into 2n minus 1, and we got this. When we factorize, we take out the c. Yes? So this algorithm will be of the order of log n, we keep dividing by 2. Right? So so this recurrence examples, I don't think it's on the slides, so I'm gonna take it and load it on for you. Yes? So it's there, you could get that to download. And this one is what? So let's just take a quick look at this. Somebody was asking about the, how you call it, the nested loops. Yes, who was asking about nested loops? See, we've seen it here. For I equal n, 1 to n, and here, so j equal I to n, and we add it up. So you get n squared from this loop. You're following the same process, and you will see, if you sit down and you do this, right, the way to do this question is, what if n was 12, or if n was 10? Then when I is 1, right, your outer loop is going 1, 2, 3, and so on till 10. And what is the inner loop doing? It's going from I to n. So over here, the inner loop will go from 1 to 10. This one will go from 2 to 10. This one will go from 3 to 10. And 4 to 10. And so on until you go 10 to 10. So how many times will this loop run? 10 times. 1, 2, 3, 4, 5 till 10. How many times will this one run? 9, 8, 7. How I get an 8? It's 3, 4, 5, 6, 7, 8, 9, 10. Not 10 minus 3. Right? 7, 6, 5, and so on until 1. So basically, if this was n, it'll go down to 1. And how much will it be if we add n to 1? See it? The exact same thing that we had. So if you work this out, all this maths here might be confusing to you. You're supposed to know it. But if it's confusing to you and you do it back to first principles, you will see is n plus n minus 1 plus n minus 2 and so on until 3 plus 2 plus 1. And when we add a series from 1 to n, what do we get? It's the first term n plus the last term 1 multiplied by the number of terms, which is n, all over 2, half the number of terms. And you'll see this gives us the exact same thing. And I use logic. I didn't use all this maths and whatnot to confuse me. You don't have to use this. You could go and do this simply using first principles or basic examples. So the people who ask me about the double loops will do the same, will see that. And if you have 3 loops, well, you'll see it, we'll have a third set. And we talk about recursion and the base case and whatnot. we did all of this. And this example is sum of an integer q. We did this like c plus t to the t of n minus 1. And they will simplify it. Binary search, we keep dividing by 2, and we get up the order of log n. See it? This is the exact same thing we did before. The only difference here is this is one constant, and this is one constant. It doesn't change the price of cuckoo. In our example, we had c here. It doesn't change anything. It's still log n, order of log n. Because I would have simplified at the end by telling you of the order of log n, which those slides didn't do. Merge sort, and we did merge sort, exact same thing. Well, you don't have to worry about Fibonacci. Of course, Fibonacci is a very simple thing. Let's go to the whiteboard and I'll show you. Fibonacci sequences like this. You start with 0 and 1, right? And that's your first term and second term. And what happens? You will add 1 and 0 is 1. So the third term is equal to the first plus second term. The fourth term will be 1 and 1 is 2. The next one is 1 and 2 is 3. The next one is 2 and 3 is 5. Next one is 3 and 5 is 8. 8 and 5 is 13 and so on. Right? So that means that the nth term, right? Term n is equal to term n minus 1 plus term n minus 2. So if this is n minus 1 and this n minus 2. So this term is equal to this plus this, and this is equal to this plus this. This is equal to this plus this. So the previous two terms will add up to give you the next term. 8 and 13 is 21, and so on, 34, etc. That's Fibonacci sequence. So you will find that see, they give you it's the order of 3 over 2 to the power of n. This is a exponential if you have to work it out. But there are shorter ways to deal with it. See, t of n is greater than or equal to time for n minus 1 plus n minus 2 plus some constant. So you can do some reading on memoization and dynamic programming and so on. So there are lots of stuff. You don't have to do everything, all right? But you need to be able to understand it. Okay? Now, there's one more thing I wanted to explain to you. NP problems. Okay? And we're almost done. See, it in 7 o'clock yet, and we're nearly done. So I'm going to share you NP problems. What is NP? You can't do a course like this and not know NP. Now, you don't have to know everything. I just want you to understand. Okay? Because more than that is a master's level course. You see this kind of numbers when you start with 4 and 6 something, and 5, that's master's level courses. So I ain't teaching you master's level thing because you don't have to do the kind of problems in this. I just want you to be aware of it. But NP complete. Right? So far, we've seen a lot of good news. Right? Such and such a problem can be solved quickly in close to linear time, or at least a time that is some small polynomial function of the input size, like n squared, n cubed, log n, and so on. NP completeness is a form of bad news. It is evidence that many important problems cannot be solved quickly. NP complete problems really come up all the time in day-to-day experience. Why do we care? Knowing that they are hard lets you stop beating your head against the wall trying to solve them. Right? But when you're trying to solve them, use a heuristic, some kind of guideline, some kind of common sense thing. Come up with a method for solving a reasonable fraction of the common cases. or solve approximately. Come up with a solution that you can prove is close to right. It's not the optimal or the perfect one, but it's close to right. Or you can use an exponential time solution that will take really, really long, right? If you really have to solve the problem exactly, and stop worrying about finding a better solution. So these can be found in optimization and decision problems. Optimization and decision problems is like, remember we talk about greedy algorithm, you're making a decision at a point in time, or optimization problem, you want to maximize profit whilst minimizing expenses, or like you're in a truck, you want to maximize the amount of case of beers you could put on the truck, while minimizing the size of the truck. See it? So it's very scientific. Those trucks that are driving around and the size and the design and thing is not by coincidence, Those things were scientifically decided upon. When Carib factory decided on the size of bottle and case and whatnot and thing, they don't have control over the size of the truck, but they have control over the bottles and the cases. So they could decide, well, the size of the can is so round but higher. So you have some people have tall, thin cans and other people have short, fat cans. When you go in the grocery, you see all kind of different sizes. It is not random or vice versa. They work out their process, how they want to fit it, how they want to stack it. Because with carib, there's a certain amount you could stack, otherwise the weight will crush it. Now, if you look at peas and carrots and so on, those cans are stronger. They made to last longer. Beers are made to last forever, but cans make to last donkey years into nuclear war and thing, right? So they're stronger and they can last much longer. The expiry date will have a much longer time than a can of beer or a bottle of beer. They're very scientific in how they do it. Whilst you're not doing the science, right, and you're not doing the calculations, your programs might have to support those processes. So optimization problem is to find the best value, while decision problem is to come up with a yes or no, right? So should we go ahead with this project? Yes or no? What are the things we think about? Optimization problems can be cast as decision problems that are easier to study. Example, shortest path. You get a graph with unweighted directed graph and you want the shortest path. Find a path between U and V that uses the fewest edges if it's unweighted. If it's weighted, you might want the total to be least. Does a path exist from U to V consisting of a rhythmic complexity and so on? You could look at those. You should know about those things now. Now, there's a class P consists of decision problems that are solvable in polynomial time, right? So polynomial time algorithms, their worst case running time is of the order of n to some power of k, some degree. Non-polynomial time is like when n is in the power. So this is exponential. Look at this one, n to the power of n, and this one is factorial. We know that these are crazy times. So the problems with these, that was the one like knapsack and the triangle problem and the LCS, and all those are non-polynomial time. So you have some problems that are tractable and intractable. Tractable means we could solve it, as in P. And those are not in P are intractable or unsolvable. They can be solved in reasonable time only if the number of inputs is small, or they cannot be solved at all. And non-polynomial algorithms always worse than polynomial algorithms, not necessarily. Brute force, yes, right? And then you could see it could take really, really long. And n to log n to the power of log n to the power of log n is technically intractable, but they're real easy and it'll solve real fast, right? And so on. So they give you examples, and you could go and read up on some of these things and understand what it means. You're not getting tested on it. You could just take a read. And when it gets too complicated, just stop. Okay? If you understand further, that's fine. I don't need you to know all of these. This is master's level. Okay? This was just to give you an example and let you understand what are NP problems, non-deterministic polynomially. Okay? Now, so we could thing out our rule here very quickly. So we have Aaron, Adam, Hakeem is Anastasia here, yes. Dominic, Dwight, Jada, Jeremy, Josh, Josiah, Justin, Kevin, me, Megan, Mikhail, Nikita, Owen, Saeed, Sophia, Samira, Sophia, Sonia, Terry Jo, Troy. And did we have Christopher earlier? Yes. So everybody's here. That's excellent. Thank you guys. And let me just last week I told you I gave you tips for your final exam, but I will just remind you again today. Quick. All right. Make sure the exam don't come up on the screen.
Sir, excuse me, is it the exam up on the screen?
I say I'm making sure it don't come up on the screen. Yeah. But so you're getting a question on Dijkstra's algorithm, and all the information you're putting and doing it is just like how it was done on the video. So you follow that video and know it really well, right? And you don't have to answer it now, but does Dijkstra's work with negative weights? We talked about that last week, right? Then you have to know Kruskal's and Prim's algorithm, just like on the slides and the PowerPoint presentation and what have you. And you have to be able to find the minimum spanning tree and draw the minimum spanning tree. And you have to know the orders of the algorithm and why is it so and so on, right? And remember, there's a slide now. You know, Prim's algorithm and Kruskal's algorithms are two different algorithms to find the same minimum spanning tree. So you should know what is same about them and what is different about them. And all of that is on the slides. And you also have to know LCS, right? Longest common subsequence. You have to know about brute force. You have to be able to actually use the algorithm. You have to know the code, right? If I tell you write an algorithm, you have to do it in pseudocode. Or remember I gave it to you, have those pseudocode on the presentations and so on. If I ask you to describe an algorithm, is you say it in English terms, like if you're telling somebody about it who didn't do this course. And you have to know the order of the algorithm and how we get that as the order of the algorithm, what makes it that order, right? So you know in graphs, what's important is the number of edges, the number of vertices, right? In LCS, the number of characters in one string and the number of characters in the other string, the M and N and thing, right? So you'll have to explain that. All those things are on the slides, guys. And then I will give you a bit of code and you have to say what the code does in English, right? You don't have to go and explain each line. Like how we had another one where the algorithm, it finds if two numbers add up to some other number, two numbers in the array add up to some value X. Or if there's a number bigger than the other one, or it finds the total in the algorithm, or it takes the smallest and move it to the top, and so on. What's the
So that's
complexity?
like the,
Uh-huh.
that's like the question in quiz too.
Yes.
You see, yeah.
Right. And you also have to know when you work out, when I give you the code, you'll have to use the code, every line in the code, and count the number of operations as best you can and work out the time complexity. And then you will have to describe an algorithm that does it more efficiently. So usually more efficiently mean if something is n squared, then you have to do something in n. If something is n, then you'll have to do something in log n. That kind of thinking, right? And the code I'm giving you now, when you come up with the algorithm that's more efficient, you might just have some minor modifications to make in the code, right? And here's a hint. The algorithms you're getting is one that we actually do in class. The pseudocode we actually do in class. I'm not bringing something you never see before. So if you mess it up, that's because you didn't do your work at class. And it means that next year, January, you'll come right here and hear me teach the same thing over and over again. And oh my God, that is going to be so freaking boring. Yes or no? So if you don't want to come back in front of me next year and hear the same thing over and over and over again, do what you have to do. You're getting a question on knapsack algorithm. Okay? All the questions in that, just like how the questions done in the past paper, just so it's going to be here. So make sure you can do those things and answer all the parts. You're getting a topological sort. Okay? So 6 questions for a total of 100 marks. All right? Any questions, guys? I try real hard to explain everything as much as you need to know and as best as I could. The rest was for you to put that effort, okay, guys? So, your exam is 3 weeks away. 3 weeks. So you have time to go and really pound some work and do that past paper. Here's what I'm gonna do for you, guys. Because I really want you to pass, I don't want anybody to fail. I put last year's paper for you. Okay. I am going to put the year before for you. Did it have an exam the year before? Seriously, I ain't seen none. Apparently, you didn't have none in 22. Okay. Nope, you didn't have any exam in 22 because of what do you call it? COVID. But you had one in 23, which I'll give you. Let's see if you had one in 2019. Yeah, so you had one in 2019. So I'm gonna put that paper for your final exam. 2018 to 2019, yes. Right, so I'm gonna load that paper for you. It's now on the files. Okay, so now you have 2 exams. And if you do all those past paper questions and you learn everything in it, that means that you would have covered what I taught in class. Okay, so the rest is up to you guys. Please, please, please do some work and come. In terms of dynamic programming, would the coin problem be a question on the exam? Well, coin and knapsack is 2 different problems. Knapsack coming, coin incoming. You would see coin show up in our previous paper. Why we did coin problem and binary search and the finding the page in the textbook and thing is to show you that you could do the same problem in different ways. And in the past, versions come, the questions and them come wearing different clues. So like people get the same question as the coin problem, but it wasn't with coins. Okay, and I did the same coin problem with you as well, but not with coins. I do it with coins and then I did it with something else. The trick is for you to recognize that it is the same problem. That is where your skill and intelligence and application of yourself to the material comes in. Okay, and remember in the beginning, I told you this course will be one of the toughest ones that you do. But if you do what I teach you and what I tell you to do, you'll have no problem passing. So if you apply yourself and you do the work, you shouldn't have trouble because I did not make it totally Greek and totally different and so on. So by the time if you do those 2 past papers, work together in groups, 2, 3 of you, not 5 and 10. 2, 3 of you max and work it out. And you get in trouble, well, you could call in somebody else to help you and guide you through it. Okay? But if you have 10 people all the time, you'll end up making more noise than study. So try that approach. You all have Zoom now. When I was your age, we didn't have Zoom. You know, we had to meet up in school and be in UE all till 2, 3 o'clock in the morning and sing. I mean, literally breaking good 3/4 the night on campus and so on before we go home. Only to go home and depart by ourselves. Any other questions, guys?
Yes, sir. The last question I have before we dismiss, right? When it comes
You
to
promise?
the situation where, can you hear me?
Yeah, I'm just kidding. I'm just kidding. Go ahead.
Yeah. When we come to describe an algorithm in English terms, right? You
Yeah.
said for like someone who didn't do this course, but when I come to answer these questions, I'm in the habit of saying if it's divide and conquer, if it's naive, if it's brute force, and
You
if
can do
it's
those, that's
greedy.
fine. You can discuss that. But make sure I understand step by step what is to be done. Right?
Right. I was just making sure that jargon is not too technical.
Right.
Because you said for someone
Yeah.
not to
It's
understand.
not, you're not translating code into English. Okay? Yeah.
Mhm.
Good?
Well,
So
I think that's it for me. That's the
yeah.
only question I had
Anybody else?
for the final.
I really hope you enjoy doing this course. I hope it's not as much stress for you. Don't make it stressful. Just apply yourself. And I think last year everybody passed, you know, if I remember correctly. Or almost everybody. It's just minimal repeats. And that happens sometimes, not because the material hard, you know. Very often the people who repeat are people who might be working or they have kids or a combination of that. I know one lady who did this course about 4 times, right? And one year it was job work related. The next year she failed because she and her boyfriend broke up. I hope I'm not talking about anybody in this class, I promise. So if you went through these experiences, trust me, it's not about you are talking, right? Eventually the lady did pass, so she has moved on. So the next time, I think she had more trouble with somebody, and then another time she had a baby. So no, 1 year she was pregnant. So she had to deal with having this baby, and then the next year she had the baby, and she had problems with baby daddy and whatnot and thing. So that was quite a while back and so on. That's just one example. And then you have other people who work, they get promotion, and they're so busy now meeting those responsibilities, they're not getting time to study or to apply themselves. But at the end of the day, even if you have a good excuse for failing, it's still just as painful. You still have to pay the same amount of money to repeat. You still have to go through the process again. You still have to be here extra year, and you don't want that to happen. Okay? So I really wish you all good luck. I want the best for you. All right? It's possible. You go ahead and get your work done. Make sure all of your assignments are submitted by the end of this week. Okay? If you haven't done it by the end of this week, well, boy, that one is on you. And so try your best and get it done as early as possible. Even if you didn't get it done this week, I'm not telling you to put it off. Try to make sure and get it done by the end of this week. But if, God forbid, something happens and you're not able to do it, still submit it next week and send my email telling me you submitted, so I could go and look for it. Okay? But if the exam reach, how I finished mark all of these assignments and you didn't submit it yet, you'll just not get it marked. And that will make a big difference to your final pass mark. Okay, put effort. Thank you all very much. I hope you enjoyed the material.
So,
Yes.
so I'm by the neighbor right now, right? I have flow issues and I'm by the neighbor catching their Wi-Fi and I was not
Okay.
there for the first hour of your class. Did you make any mention as to uploading the previous videos of the past sessions?
I've
By
been
any
trying,
chance?
remember, I don't have all recorded, right? But I put up some, I have not been able to get all done, but I am going to try to get the rest done. Maybe I'll get it.
Yeah.
I have a meeting tomorrow. I have on Wednesday morning and Wednesday evening. Plus I have classes. So I'll try to get that done before the week is out.
Oh boy,
Okay?
busy man. Yeah, man.
It's
you're a
really,
jack of
really
all
tough.
trades.
I had a meeting in Port of Spain this morning, and I reached back
Oh.
home after lunch, and then I had class this afternoon, so you could see how things
Yes.
going. Plus,
I
I
was
have
happy.
other administrative stuff to do. It's really,
Right,
really
right.
tough.
Well, two of
But-
the classes will be missing, I'm aware, because we had 2 physical classes. That's fine.
Right. So I'll try to get the others as best as I can, okay?
All right,
Yeah.
thank you very much.
All right, guys, take care. Have a good evening and good luck till the exam. Bye.
Thank you very much.
So, bye.
Bye.
Present.